All right, so let's take a moment here and look at one of my favorite types of dynamic problems. And I like just to call these elevator problems because we're dealing with an elevator and someone in an elevator. So what's great about elevator problems is, well, first, there's only one dimension, right? Because the elevator is just moving up and down. So that's convenient. And also, the key to solving these problems is basically once you draw a free body diagram, the rest of the problems typically just kind of fall into place. And the free body diagram overall is pretty simple. So I really do like elevator problems. The way you can make these problems a little bit more complicated is maybe you're analyzing the motion from a graph first and then learning information from that, but overall they're not bad. Okay, so let's just look at the problem first before I gush about it too much. Okay, so we've got Alice, and Alice has a mass of 70 kilograms. So let me just write that down. All right. She's standing on a scale in an elevator. As the elevator stops, the scale reads 750 newtons. All right, so 750 newtons. Question is, what variable do I assign that? Okay, so this is what a scale reads. Now, so this is a bathroom scale. Bathroom scales, they measure the normal force. All right, so I like to think of scales as normal meters. So when here it says sorry about that. I think I was talking about bathroom scales. Bathroom scales read the normal force. So the normal force here is 750 newtons. Sorry for my dog whining in the background. Right, so normally if you're just on a stationary bathroom scale, right, you say, oh, it's measuring my weight, not the normal force. Well, it's measuring that situation both because your normal force is equal to the weight because this bathroom scale is not accelerating. Here, the bathroom scale is in an elevator, so there could be acceleration going on, which is going to affect our reading. So in this situation, sorry, there's a dog outside, so my dog is whining. Reads the normal force. All right, so questions here are, had the elevator been moving up or down? And if the elevator had moving at 5 meters per second, how long does it take to stop? All right, so the elevator had been moving, we'll worry about that in a second. We'll write speed being 5 meters per second, and we'll deal with that in a bit. And how long does it take to stop? All right, so elevator problem, our first instinct should always be drawing a free body diagram. So here is the person in our elevator, or we can just say the elevator itself, or the scale, doesn't really matter. So acting on the person in the elevator, well, the person always has the force of gravity acting on them. That's pointing straight down. And force of gravity, well, that's mg, right? Where mass is 70 kilograms, so it's about 700 newtons, right? I'll use 10 meters per second squared for g. Well, that's pointing straight down. Now, the other force is the normal force, right? The force of the scale on the person, and that's pointing straight up. I drew that bigger because we see that value is 750 newtons. All right, so what we've learned here is that the net force is upward, right? So that implies an upward acceleration, right? Well, we can reason then, if acceleration's upward, we can look at the problem and it says, as the elevator stops. So that means that the elevator is slowing down. If for an object slowing down, its velocity and acceleration have to point in opposite directions. So if our acceleration is upward, which it is in this case, that means that our velocity has to be downward. So this elevator is moving down. Let me just write that down. All right, so I wrote down my reasoning there. Now, next question here says, if it had been moving at 5 meters per second, how long does it take to stop, right? So this part here reads, let's use kinematics. But every kinematic equation involves acceleration. So we need to determine the value for this acceleration, which is where, using forces, Newton's second law in particular is useful. So let's call upward our positive y direction. So if I sum my forces in the y direction, well, net force is mass times acceleration. All right, so going from there, since upward is positive, we have a positive normal force and a negative gravitational force. So that's, let's use variables. Positive normal, negative gravitational force is mass times acceleration. So then solving for acceleration, we just take normal force minus the weight divided by mass gives us acceleration. So, oh my god, my dog won't be quiet. It doesn't matter. Okay, so normal force minus gravitational force, that's 750 newtons minus 700 newtons, giving us 50 newtons up top, divided by the mass of 70 kilograms. So we have 50 divided by 7, so 5/7, which is about 0.714 meters per second squared. Okay, so then, now that we have acceleration, we can use kinematics to find the time. So since we know the initial velocity being our 5 meters per second, we know the final velocity is 0. So let's use the velocity equation. So final velocity is initial velocity plus acceleration times time. So we know our final velocity is 0. So we end up with initial velocity divided by acceleration gives us time. Forgot the negative sign there, apologies. The only thing we have to be careful with here is, since we're calling upward positive, its initial velocity, since it's moving downward, is a negative quantity, so we have negative times negative 5 meters per second, divided by our acceleration we just computed, 0.714 meters per second squared. Looking at my units just to make sure it all works out, it does. Meters per second divided by meters per second squared gives us just a second in the numerator. And this gives us around, well actually, if I kept it as 5/7, we can see it a lot easier. It just gives us 7 seconds. So it takes 7 seconds for this elevator to stop. All right. So kind of the whole trick in this problem, it might, when you first look at the prompt, it might be like, well, I have no idea which way it's moving. How do I figure that out? Draw a free body diagram and just realize when it talks about the scalar reading, or maybe it'll mention that this person has an apparent weight of 750 newtons, right? Apparent weight is what a scale reads, and that is the normal force. And then everything will come together after that.